In this section we're going to look at the parametric equations for the parabola y squared equal 4ax. It turns out to be much easier to solve problems if we can write down parametric forms for the tangent, normal and so on, rather than the Cartesian form. Now I've written down the parametric equations that we're going to use at the top. Basically any point on the graph, y squared equal 4ax, we can say that the x coordinate is of the form at squared and the y coordinate is of the form 2at. There will be other parametric forms that we could use, but this is the simplest version. And we can easily check by substituting x equal at squared and 2at into the parabola, or this equation, and check that with y being that and x being this, it is satisfied as shown. That means that this point always lies on the parabola. Conversely, one can show that every point on the parabola can be written in this form, except one particular point, which is the origin, as we'll see later, but of course the origin is also on this curve too. The second thing we're going to determine is the gradient of the tangent at the point at squared 2at, and that turns out to be 1 over t. So the parameter t in this at squared 2at parametric form represents 1 over the slope of the tangent to the parabola at that point. We could actually check that if we wanted. As we see here, if we use the chain rule, we can work out the gradient dy by dx as dy by dt times dt by dx, and dt by dx is 1 over dx by dt. Substituting y equal 2at and x equal at squared into the two expressions on the top and the bottom, we find that the gradient at that point is indeed 1 over t. So how do we get that parametric form? Well, we'll quickly have a look at that, but the important thing is the result. So on this graph I've shown y squared equal 4ax and a general straight line y equal mx plus c. What we're trying to determine is the relationship between m and c for which this straight line is a tangent to the parabola. Now quite obviously, if it's a tangent, then there is one point of intersection. The cases where we have 2 points of intersection would happen for this line and no points of intersection here. So we're going to determine the relationship between an m and c for which this straight line is a tangent by insisting that the points of intersection here are coincident. So by eliminating between y squared is 4ax and y equal mx plus c, either y or x, we get a quadratic equation in either x or y. In this case I've multiplied the equation of the straight line by 4a and then replaced 4ax by y squared, so we get a quadratic only in y. This quadratic has roots which are represented by the y coordinates of the points of intersection. If we only want one point of intersection, so a tangency point, then we want equation 1 to have equal roots. For that to be the case, then what we need is this coefficient squared to be equal to 4 times this times this. In other words, the discriminant equals 0. So if we work out what that expression is, which is here, and then simplify it, we get that y equal mx plus c is a tangent to the parabola, provided the intercept c is a divided by m, a divided by the gradient of the straight line. We can then work out what the y coordinate is of that point, and that's easy to do. If we use the formula for the roots of this quadratic, in the case where c is a over m, we determine that y equal 2a over m. You can check that. What I've actually written is the fact that it's the half of the sum of the roots, and if both roots are equal, they are this value here, again determined by solving equation 1, in the case c equal a over m. We can then work out the x coordinate from either the equation of the straight line or the parabola, and this last line tells me that x is a over m squared. What that means is that the point of contact of a tangent to the parabola will have form a divided by m squared, obviously provided m is non-zero and the y coordinate is 2a over m. So what we've shown is that y equal mx plus c is a tangent provided c is a over m. In other words, the equation of all tangents are of this form, provided m is not 0. And m equals 0 would give you a straight line which was horizontal, which is never going to be a tangent. And secondly, the coordinates of that tangency point are a over m squared, 2a over m. And of course the gradient of the tangent is m. If we, rather than using m, use 1 over m and call it t, then the gradient becomes now 1 over t for the tangent. The equation of that tangent excuse me, is this. But more importantly, because we're setting t to be 1 over m, the parametric form here becomes at squared 2at. So that in summary, at squared 2at and represents a general pair of coordinates for a point on the parabola, and t represents 1 over the gradient of the tangent at that point. And if we wanted it, this is the equation of the tangent.